Hello and welcome to a coding challenge. So this coding challenge is called, I think, Attraction and Repulsion. So I'm recording the intro after I did the challenge. It was kind of a mess and I never really got to the result that I wanted, and I just sort of played around with a bunch of different possibilities. So I'm asking you, the internet, to, are you the internet? I'm not sure who the internet is. Maybe it's you. I don't know who it is, but you're watching, to take my code and hopefully expand on it and improve on it in interesting ways. So what I was imagining was creating a lot of interesting attraction patterns by looking at the trails of various objects as they move and get attracted to different attraction points within a canvas. And you can see if I just kind of Google image search attractors and processing, we're seeing a lot of visual images like this. So you can imagine dropping a whole lot of particles into a space, ignore this image of me behind me, and having them sort of swarm around and move around all these invisible attraction points. So where I got to with the challenge is kind of an end result that looks something like this. And what I actually started doing was just showing in the challenge towards the end, I decided to show you the difference between attraction and repulsion. And if I add a bunch of these all around, you can see what's happening is every single one of these attractor spots attracts these particles that are just entering the scene, but when they get within a certain number of pixels of the attractor, then they're repelled with a very strong force. So this hasn't really produced a visual result necessarily that I'm happy with. I would be interested to see what happens if I looked at the alpha blended trails over time, but this example that I end with should have all of the pieces for you to take and add your own design, creative spin on it. So watch the video, you'll learn a bit about how vectors work, how forces work, how you can add different objects with the mouse, with arrays, and looking at how you can accumulate different forces and have interplay between different particles moving around the screen. And the mechanics of it will be there in the video. I'll make lots of mistakes and get confused. And then at the end, you'll look at this video's description, find the code, and hopefully expand on it and make something much more beautiful and much more interesting, because I really failed at doing that. So I hope you enjoy this coding challenge. I guess I have to, at this point, I have to blow the train whistle. It's like I have a contract, which doesn't exist, but it says in there, blow the train whistle. So that's what I've done. Enjoy the coding challenge, and maybe you'll still be watching at the end or in the next video, or you might run away forever and never come back, which I would totally understand. But anyway, goodbye. See you soon. All right, let's get started. So actually, let me come over to the whiteboard. The first thing that I need to do, basically, this is what I need for this example. I want to have two kinds of objects in my world. I want to have something that is an attractor object. And honestly, I don't think I need a full-on attractor object in this case. The attractor can actually just be a single vector, right? All I care about for the attractor is its XY location, where it is. So I want to have an attractor, that's a thing that's drawn on the screen, and then I want to have particles. So I want a single particle, which is like a dot, and I want that dot to be attracted to the attractor. And how do I want it to be attracted to the attractor? By using gravitational attraction. So the formula for gravitational attraction is the force of gravity, expressed as a vector, is equal to g, which is the universal gravitational constant, the gravitational constant. The universal gravitational constant, g, times the mass of one object times the mass of another object divided by distance squared. The truth of the matter is, I think I could consider the mass of this particle as 1 and the mass of this attractor as 1. So if the mass of both of these are 1, then my formula becomes g divided by distance squared. So really the force of gravity, I'm 1 with the force is 1 with me, the force 1, something like that. Anyway, the force of gravity is really just a constant that we're going to make up. Is it strong or is it weak? I mean, this is a real number in the real world in physics, but we're living in this fake pixel space, so I'm just going to make up g. And then we have this interesting question of, should the force's strength be proportional or inversely proportional to distance? So what this means is, if the particle is really close to the attractor, it's going to be really attracted to it. If it's far away, that attraction is going to be much weaker because I'm dividing by the distance squared. So as you maybe make a creative project out of what I'm showing you in this video, you might play with this idea. Maybe it's weaker when it's closer, it's stronger when it's further. Let's just sort of give it a try. And then obviously at some point, we could make this force not attraction, but repulsion by just multiplying all this by a -1. So anyway, let's go back to the code and start implementing some of this. So here I am with the code, there you are, and I'm going to start writing some code. So I'm going to go over here, and I have I have a particle, I have a separate JavaScript file called particle.js, where I'm going to create a constructor function with a particle, and I'm going to just give it an x and y. So the only thing I'm going to give to the particle when it starts is a location to start, and I'm going to say this.pos equals create vector x comma y. So now I have a particle with a position that's a vector of an x and y. Now, in the main sketch, I'm going to say var attractor, and then I'm going to say attractor equals create vector 200, 200. Now I could make an object for the attractor like I'm doing with the particle, but right now my attractor is just going to be a thing that stays in one place. It doesn't need to animate, it doesn't need to keep track of a color, so just a single vector is fine. Then I want to see that everything's working, so I'm going to say background 51, and I'm going to draw maybe, let's just use points for simplicity. Stroke 255, stroke weight 4, and I'm going to say point attractor dot x, attractor dot y. And let's just take a look at this real quick. Hit refresh, and there you go. There's my attractor. The dot in the center of the window. Yes. Okay, so that's working. Now, what I want to do is add a particle. And I want to say a particle equals a new particle, and I'm going to put it at, I don't know, 200 comma 100. And then I want to say something like particle dot show. Now, I have a constructor function, so that'll work. I do not have a show function. So right in here, I need to say this dot show equals function, and I'm just going to also do the same thing. Stroke 255, stroke weight 4, and then point this.pos.x, this.pos.y. Now I realized something I forgot to actually reference the particle itself in the HTML file, the particle.js file, so I'm going to do that real quick. Okay, great. Now, what do I have? I have a particle and I have an attractor. Look at that particle, look at that attractor. Attract the particle. Okay, so I guess I can't do it with motion in my hands. We've got to add some code. So let's go back to the sketch. And what I'm going to do here is I want to say particle attracted to attractor. So I want to have some generic way of saying any given particle can be attracted to some vector. And so I'm going to write a function in the particle object called attracted that receives an attractor. So let's take a look at that. And let's go to the particle. That means I need a function. This dot attracted equals function. And that function, I'm going to call it target. So I'm going to give the argument a target. The target is the thing that's attracting it. So we're getting somewhere now. But one thing I realized here is that I don't even have a way for this particle to experience any physics. And so if you're interested in the sort of larger topic of physics engines and the kinds of physics engines you can build, the kinds of physics engines you can use as separate third-party libraries, I've got a lot of videos as part of the Nature of Code course about all the steps, which I will reference in this video. But right now I'm going to do this in a really quick way using something called Euler integration, often mispronounced as Euler, but it's Euler. So what I need is I need to integrate, meaning I'm doing this thing where I'm saying, how does position change over time? This is actually, what's the rate of change of position or the derivative of position? It's this dot velocity, and I'm going to make a vector 0, 0. Then I'm going to make a vector which I'm going to use as acceleration. Create a vector 0, 0. And actually, by the way, if you just say create vector with no arguments, it makes a vector 0, 0. What is a vector if that's not familiar to you? I'll point you to also reference a video that goes over the basics of vectors. So I have position, velocity, and acceleration. Now what I want to do is add a function. Maybe I'll call it update. Could call it step. All physics engines need a sort of moment. You step through time. What is that time? How many cycles of time are you iterating through depending on each frame of animation? I'm doing this in a simple way. Every frame through draw, every frame of animation in my sketch, I add velocity to position, and I add acceleration to velocity. So now, if I were to actually give a velocity 0, 1, and I were to go to the sketch and also say particle.update and run this sketch, we can see, there we go, my particle is moving towards the attractor. Now, I just happen to give it a hard-coded velocity pointed straight at it. So if I go back to the particle and I say something like, -1, 0.2, you can see the particle is moving over that way now. So the velocity is a vector that controls how that particle moves. I could also give a particular acceleration like 0.01, and you can see now it's accelerating down, right? Because that acceleration is accumulating onto it. So this is a very basic physics engine. I have a particle that has a position, it has a velocity, which is an arrow that tells the position where to go next frame, and I have an acceleration which tells the velocity you should turn, you should slow down, you should speed up, and that's happening here in this update function. Now, if you recall, I said here's this thing called a force, and the force is a vector that is going to, I want to have this particle be attracted to the attractor wherever it is. So I need to calculate a vector that's always pointing from this particle's location towards the attractor. And how do I do that? So the easiest way to get an arrow that points from one position to another position is to subtract those two positions together. So this is where I'm going to start. What I need to do is write in that attract function, I need to figure out this force. There's a bunch of things going on here. So there's three things. One is I need to figure out this force. So I need to know how do I get an arrow that points from the particle to the attractor. Then I need to figure out how big should that arrow be. Is it a weak force? Is it a strong force? The strength of it is coming from this formula that we're kind of working out over here. But beyond that, I'm saying it's a force. And if I come over here, position, velocity, and acceleration, what's the relationship of force to position, velocity, and acceleration? Well, you might be familiar with Isaac Newton, and there's a bunch of laws. I'm sure they're all very important and interesting, but the law that I'm interested in is force equals mass times acceleration. And what did I say about simplifying our world to just make the mass of everything 1? Yeah, so if the mass of this is 1, then really force equals acceleration. So force is a vector that causes a mass, a force is a vector that causes an object with mass to accelerate. And so we can actually just, if I could figure out this attraction force, then I could just put that right into acceleration, and our simulation is going to do exactly what we want it to do, I hope. Okay, so I'm coming back over here. Use the force, I think is the proper terminology here. Use the force. Okay, now I've lost my train of thought. Okay, so let's put all this stuff back, so to speak, empty vectors. And let's come here. So how do I do this? What did I say? I need a vector that points from the particle's position to the target. The way I get an arrow that points there is I say target minus the particle's position. So I'm going to say var direction equals p5.vector.subtract target minus this dot pos. Now, this is just about the most awkward way I could ever possibly think to write this, but just for the sake of argument, I'm going to put here in the comments, I'm going to put a comment var dir equals this target minus this dot pos. This is really what I want to do, right? I want to say, give me a direction, a vector that points from the position to, from the position to the target by subtracting the two positions. But the minus operator doesn't work with vector objects in JavaScript. In other programming environments, you can kind of overload the operators and do fancy things. So what I need to do is use the subtract function that's part of p5.vector, and this will give me a new vector that is a result of target minus position. Now I have a vector that points all the way like this. So the question now is, how big should that vector be? Should it be short? Should it be long? Should it be medium? And there's lots of ways you could decide. I'm going to use this formula. G divided by distance squared. I'm going to consider the mass, so I want to have it inversely proportional to distance. So let's figure out how we can do that. Now, one thing that's nice here is this vector that points all the way from one object to the other, that is the distance. And actually, I can just get distance squared is the direction, that vector, the length of it is distance. And if I want distance squared, there's actually a function, I believe, in P5 called mag SQ for magnitude squared. So this is giving me that value, distance squared, that's on the bottom of our calculation. Now, I also need to figure out what the universal gravitational constant should be. Let's Google the universal I really want to get tickets to the universal gravitational concert. I can't even make my bad joke. So if anyone could get me tickets to those, I'll take Hamilton tickets too, that's fine. So this is the universal gravitational constant. Let's use a little bit of something from that in our code just for fun. So I'm going to say, again, I could just make this up. Var G equals that number. So now the magnitude is G divided by D squared. So I've got a vector pointing from target to, pointing from the position to target. I have the distance squared, I have a pretend universal gravitational constant, and now I have the magnitude. So what I need to do is say dir set mag, that magnitude. So what this set mag function does is it takes a vector of any length and keeps its direction, but sets its length to the length that I want to. So I don't like the fact that I'm going to say strength or something, because it's really the strength of the force. And I think this should really be called force, because that's what I'm doing ultimately is I'm calculating this force. So ultimately I'm starting with a force, that's the full distance, then I'm getting the distance squared, making up a gravitational constant, calculating the strength, and setting it. And now what do? Acceleration equals force. So in this case, let's take a look and see what we've got. So now, if I call particle attracted, particle update, and particle show, I should calculate a force in the attracted function. That force will go into the acceleration, which will then go into the velocity, which will go into the location, which will update its location, and then we'll draw it. Here we go. And sad trombone. Oh, okay. This dot, it's always the this dot acceleration. Let's just hard code the strength for a second as 1. Oh, it's working. So there we go. We can see now that it is experiencing that attraction. It's just, I got to really think about the sort of scaling of this. So it's very, very weak. Do you see how it's moving just a little bit? Now it's getting closer, so it's going to get stronger and stronger. So this is really like, I got to really start tuning stuff here. And one thing that I'm going to do, I think that's really going to help things a little bit is, one thing I could do is I could just, I want to have a much stronger gravitational constant. But look what happened just there. Whoops, let me run that again. The issue is, boom, explosion. That force was so strong. In the Apollo moon missions where they had to figure out how to go around the moon, calculate the physics properly, and slingshot to get back to Earth. Well, I've got a sort of very extreme version of that happening here. So one thing that I think would be helpful to do is to constrain this distance squared value, because you realize once that particle is so close, the force divided by distance squared is so big that that's just going to spin out of control. So I'm going to say distance squared equals constrain itself between, I'm going to say 25 and 10, what's maybe, I don't know, 400 or something. So, or 500. So I just don't want, I always want that force to be at play and don't want it to get so big. And now let me do this. So now we can see I now have a particle that's attracted to this particular attractor. And you can see that getting some interesting behavior, but really I've done barely anything yet. But this attraction is working. Okay, so now let's try to do some stuff that's a little bit more interesting. So for example, let me at least give this vector a random velocity to start. And we'll see, so now it actually has a random velocity to start, so it's not pointing directly at it. And the other thing that I want to do, I think, which would be interesting to see, is kind of draw some trails. So I'm going to put background here. And so we're going to see sort of its path a little bit more. So now what we've got is a single particle drawing a path as it kind of orbits us. Now, interestingly enough, another code challenge I wanted today was this rose petal challenge. And strangely, the attraction is giving me this nice kind of oscillating pattern behavior around the actual center itself. Okay, so let's try to be a bit more thoughtful about this. First thing I want to do is I'm trying to decide whether I want to add multiple attractors or multiple particles. But let's add multiple particles first. So let's make an array for the particles. And let's add all those particles to that array. Particles.push, new particle. I'm going to just start them all in the same spot. And then same exact for loop. Oh, I don't need it for the attractor. And I can say var particle equals particles index I. So this is me now having a bunch of particles and having them all do the same thing. And what did I get wrong here? I don't see an error. I don't have a length yet for the particles. That's a good point. Let's see, how many do I want to add? Let's add 50. And we can see there's all my particles all being attracted. They all started with a slightly different initial velocity, so they're all going to have a different pattern. And I think it's so extreme what I'm seeing here, so I want to just draw them with a lot of alpha. And we'll sort of see these paths that they're creating. Okay, so let this run for a little bit. You can see now that I've got something. Everything is really, because of the constraints that I've put in it, everything is and they've all started in the same spot, and their initial velocity is all the same, and their masses are all considered one. We're really getting a very, very uniform, almost like nucleus electron-like kind of pattern here. So this is just a beginning point. Now, let's think about what happens if we start to add multiple attractors. Actually, I want to vary this a little more before I do that. So one thing I would like to do is, I think I would like to give the magnitude of its initial velocity something that's a little bit more variable, just to sort of see. So this now is going to be quite a bit more variable. So the initial velocities, some of them are much stronger than the others. And I think just to look at it for right now, I want to be able to see the paths a bit more. So you can see here now everything is circling and being attracted. Okay, I don't know if I actually like it. It's kind of a bit of a mess now. I almost liked it better when it was much more uniform. But what I would like to do now is add multiple attractors in multiple places and see how that works. So let's go back, first of all, to just a single particle and have the particle once again have very little alpha. And we can see here's my single particle being attracted to this particular attraction point. Now what I want to do is add an array of attractors. Okay, so I'm going to go to the sketch and I'm going to say attractors equals an array. And now I'm going to say also the same exact thing for the attractors. What I want to do is say attractors.push, create vector, and here I'm just going to give them a random location, random width, random height. Okay, so now here I want this exact loop, attractors.length, and I want to say attractors index I and attractors index I. So I just want to see, I'm going to comment out the particles for a second. I just want to see, does this get me a bunch of attractors on the screen? I missed. Attractor is not defined. Where attractors, S there. Okay. So I only see one. Did I? Oh, because I only made one. Let's make 10. Okay, so now you can see this is each time I refresh the page, I get a random assortment of these attractor dots at different spots. So now I want to see if I can have the particles accumulate their attraction to all of those points. Okay? So here, notice how I had particles. So what I could actually do here is when I'm looping through, there's so many different ways I could do this, but I'm actually just going to put this loop of the attractors inside the particle loop. There's a bunch of different ways you could do this. This needs to now be J. And I need to say attractors index J. Now, this actually isn't going to work, but this is the idea. There's a big problem here. So first let me draw all the attractors. Then for every particle, let me have the particle interface with all the attractors, then update and show itself. And if we do this, we should see here's a particle. Now it looks like it could be working. Kind of just left the window. Let me run it again. The issue is actually it's not being attracted to all of the attractors. It's being attracted to just the very last one. And let me show you what I mean by that. In the attracted function, here, I'm setting acceleration equal to that force. And the way that an object behaves in an environment where there are multiple forces is its resulting acceleration is the result of the sum of all of the forces at play. So you can't just say, set the acceleration to this attraction, set the acceleration to this attraction, to this one. I've just got the last one. I need to add them all together. This is known as force accumulation. So it's really as simple as me saying acceleration.add force. Now, there's another issue here. The way that force accumulation works is at every moment in time, we start from no acceleration and add all the forces together. Then we move. Then we start over from no acceleration and add all the forces together, and then we move. The problem with this is I need to make sure that acceleration is cleared out to 0 every single time. And a quick way I can do that is once I'm done with updating, I can just multiply the acceleration vector times 0. Because if I take a vector and multiply its components by 0, it zeroes everything out. So that's a quick way that I can do that. Okay, so let's see what happens now. This is now, it's hard to sort of know exactly what's going on, but this particle is experiencing an attraction force to all of the other attraction points around. I wonder if we just had 2 attraction points, it'd be more clear, or if I started with a lot of particles. So let's go back to, let's keep that, let's take this out. Let's start all the particles at the same location. And actually, I think it might make sense to start all the particles in the center. And let's try to just do 10 particles and see what happens. Boy. Oh, look at this beautiful, amazing result. Yay, coding challenge done. This is not the result that I was hoping for by any means whatsoever. Let's see if we can. I might have a mistake in the code, actually, because that's kind of a weird issue. In the chat, I'm seeing the comment, the forces are too weak for the faraway attractors. So that certainly makes a big difference here. What I would like to actually see is a different way. I want to see this layer itself, much more kind of slowly over time. So a couple things. One is I would prefer not to actually draw the attractors. So let's not bother to draw the attractors. Let's go back to the particles. And one thing that I want to do is I want to create a vector that's its previous position. And then each time after it's drawn, I want to set this.previous.x equals this.pos.x. I want to save its last position. This.previous.y equals this.pos.y, because I think it might be nice to actually connect its previous location with a line. So right now you're noticing that I don't really see its path because the dots move, when it moves quickly, the dots are so far, and I mostly just have this mess. But if I connect it with lines, it's going to be a little bit more clear. I'm going to change the stroke weight to 1, and I'm going to give it a lot more alpha. And we'll see what sort of paths I get here. So you can see a bit more clearly what I've done is to kind of get these lines. So let's run for a little bit. So I'm going to let this run for a little bit, but what I want to do is also, I think thinking about how I do this constraint is probably, so that the forces are always at play even if it's far away, is going to be kind of give it more of a dynamic quality. I could also do something where, yeah, this is, you can see now I'm getting something more like what I was hoping to get, is some more regular kind of patterns. I guess with the alpha over, like letting it run for a long time might be interesting and nice to watch, but I don't have the patience for it right now. So I'm going to go just back to the particle and draw it with a lot less alpha. And then one thing I want to do is let's go back to, I'm just curious what happens if I let the particles all start at a random location, but I actually just don't give them an initial velocity. Everything might settle into, ooh, that's kind of a nice pattern. Everything might settle into something of a regular pattern. And I'm going to do that by, I'm also going to, I'm going to constrain this a little bit more. And I'm going to also add 500 particles, which is probably going to make it run way too slow. Yeah. So this is more like what I was hoping to see. And now you can see it's too many particles and the alpha isn't enough. So let's lower that, and let's also lower the alpha a little bit more, and let's see what we get. So you can see here, I'm starting to get some patterns that might be a bit more regular. The constraint, really there's like so much tuning that I really need to do to see if I can get some more regular patterns. I also, I'm kind of, sometimes I want them to be random, sometimes I don't. Let's have them, I just want to sort of see now back to the middle. Let's try, like, this is, and then let's give them a little initial velocity. So let's try this. Oops, where did I miss? I missed something. I missed a parentheses. Okay. So yeah. So you can see that I'm going to get some interesting kind of regularish patterns just based on this, based on the kind of initial arrangement of the particle of those attractors themselves. And this is kind of what I was hoping to kind of see. Now, there's so much more you could do with this if you're more thoughtful about how you arrange the attractors, how you set the initial conditions. So many more possibilities here. One thing that I think might help us tune this and figure out how to make it produce visuals that we might like more is, let's see if we can actually position the attractors with the mouse. So what I'm going to do is just completely comment out the attractors. And I'm going to start this sketch. And you can see here are a bunch of particles all randomly positioned on the sketch. And I could even have 1,000 of them. You can see there's 1,000 particles randomly positioned on the sketch. But there's no attractors. Because once it gets to here, the length of the attractors is 0. So what I want to do is I'm going to add function mouse pressed. And I've also set the attractors now to be green to draw them so I could see them right here, which I just added that a second ago that you didn't see because I edited that part out. Okay, but what I'm going to do is add. So I'm going to say attractors. Actually, I'm going to exactly what I had here, this line of code. But I'm going to say instead of at a random location, I'm going to add the mouse location. Okay, so let's see what happens now. So there's a lot of particles. And if I now click right here, we should see everything's attracted to that particular spot. Okay, so everything is coming in and zooming to that spot. Now, let me add another one here. And we should see now that everything is both attracted to both attractors. And I would expect to see something like a little bit of a figure 8 almost style pattern around both of them. And I could add another attractor over here and one up here and one up here. And what might be helpful here to see actually is for me to, just for right now, what I might like to do is put background and draw. So we can see now, these are very alpha-y, so I got to go back to the particle object and remove the alpha. And we can see now, and we can see now the particles all being attracted to here, being attracted to, and what happens when I start to add multiple attractors. And even if I refresh, let me try to put them in a circle and see what we get. So here we can start to see a lot of interesting possibilities as these particles are attracted and they start to almost swim around in these different, and if we drew trails and thought about color, we would probably get interesting dynamics in terms of the kind of patterns that might be painted here in this surface. Now, I want to add something else. What I would like to do is think about what happens if these attractors are repulsive instead of if the particles are repelled by them rather than attracted to them. So what I'll do to do that really quickly is just right here in that attraction function, I am going to multiply the force by -1. And let's see what happens there. So I'm going to add repulsive force. Oh, let's add one over here. Now you can see quickly everything is just going to leave the window. So in that sense, not so exciting. Everything is just going to leave the window. What if, however, every other particle I click is, so when I click first, it's an attractor. Then when I click, it's a repeller. So I'm going to do that just by saying in this, I'm going to say if I modulus 2 equals 0, draw it as green, else draw it as red. So red for being a repeller. So we can see now as I click, I get green, red, green, red. Now they're all repellers right now, but the idea here is what I want to do is also change the direction of the force. So this is a goofy way. I should probably make, again, an attractor object that has a kind of weight to it. But I'm just going to pass in J right here to that attraction function. And I'm going to say if J modulus 2 does not equal 0, then multiply it by -1, or if it equals 1. It's another way of saying that. Equals 1. Then, so now, if I run this again, if I click, oops, we've got an error message. I made a mistake. J is not defined, particle.js line 34. Oh, I need to add that as an argument here. So if I click here, we can see everything is now attracted to here. And then if I add this, it's repelled. If I add this, it's repelled. It's attracted, repelled, retracted. So we can sort of see, I should be more thoughtful about how I'm doing this. So one thing is, let's make this a little bit easier to see. With the particles, I'm going to make the particles have a stroke weight of 4, so you can see them more easily. And let me think, what if I put repulsion points around the edges and attraction points in the center? Oops, I lost track of what I was doing. So there's lots of great suggestions in the chat. What I would encourage you to do is to implement, there's so many problems with what I've made here. So what I'd encourage you to do is think about how are you adding attractors? How are you adding repellers? Where are they going? How are you adding the particles? What are the parameters of the particles? How fast can they go? How slow can they go? What's the strength of the various forces? And to see what types of dynamic systems and painting systems and patterns you could possibly generate from just a system of particles and attractors and repellers. The other thing that you might do is you might have an attractor where the particle is attracted to it, but once it gets to a certain distance to it, oh, I should just do this now, it's repelled. Let's try that for a second. So, for example, what if I go back and make them all, forget about this whole I and J thing. Let's just make them all attractors, so to speak. And then here in this attracted function, if you know what I'm going to do here just for a second? I'm just going to say force magnitude equals constrain. I'm going to make this 5. That mag squared, even though it's like a nice efficiency, it kind of confused me because I'm used to thinking distance not in terms of like squared. So this I think will be a little bit easier to sort of tune it. But what I want to do is say, if that distance value is less than, if the distance value, if it was within like 100 pixels, or maybe if it's within, let's say it's within 20 pixels, then force multiplied by -1. So now I have a particle that's always attracted, but when it gets close to the attractor, it actually is repelled. And so let's see here. Whoops. D squared is not defined. D times D. And so now you can see, whoa, did I do that? Okay, let's think about this. I might have done this in a weird place. I had the times -1 there, sorry. So look at that, they get kind of like stuck right there. That's kind of interesting. That's pretty interesting. So what happens now if I add multiple ones though? There, whoa, whoa. This is kind of crazy. I don't have a lot of variation now. They're really like, that magnitude I think is so strong. Yeah, this is more what I expected. There we go. So this is kind of what I was looking for, is kind of an interesting system, I think, to think about. That they're repelled, but, and now what might be more interesting also is if I, what I'm going to do now is instead of adding the particles in setup, I'm just going to add particles. Here we go. This is what I meant to do all along. I'm going to add particles one at a time in draw. And what I'm going to do is also, I should give the particles a lifespan and have them eventually time out. There's too many possibilities here. I've lost my mind. So I think I'm going to leave it at this. Oops. Chat pointed out a really big error actually that I just had, which is that in my particle object, I'm supposed to divide by distance squared, but this is actually g divided by d times the order of operations is off. This really needs parentheses around here, which is going to massively weaken that force. And you can see now the force is much, much weaker, but it's still kind of the same idea here. And then if I put another one, it's going to be attracted or repelled. So one thing I might do kind of like amusingly is like I could change and make the repulsion force much, much stronger, which you can see it's attracted, but when it gets within a certain distance, that repulsion force is really, really strong. And then I could also sort of think about tuning the attraction force and figure out, and someone in the chat asked, by the way, shouldn't that constrain between 0? It could be, but I definitely don't ever want to divide by 0. So if I were really trying to be accurate about this, I would constrain it by like 0.0001. But I'm trying to just kind of tune it in a way that the force is, yeah, there you go. So now I made that repulsion force really, really strong. And you can see, I don't know what the point of what I'm doing is, but these things are attracted to all these different attraction spots, but they can't get close to them. And so you can see, and if I add another one right here, then I'm kind of creating these little pockets. That's kind of a nice little behavior. And you can sort of see what I've got here. I've got all this stuff trying to get attracted, but then being repelled when it's close. So I've gone off a little bit of the deep end here with this kind of attraction-repulsion thing. And I think what would probably be more interesting, or no, I've said this a bunch of times, and now this video is being edited. I don't know where my head is at anymore, but let me wrap this up. So the tools that you have now from this example are the idea of calculating a force between two positions. So the attractors are fixed, but those could be particles that move. All particles could be attracted or repelled from all other particles. So that's something you could add to this. You could think about drawing trails with alpha and picking color, where you start the particles, the strength of the attractions, how you constrain that distance, whether it's stronger when it's closer, whether it's farther. So every parameter, every variable, everything that defines how these particles move could be something that you could tweak. And so I hope that you create some type of simulations or paintings or algorithmic. What if you had an image and you kind of put attraction points all along the contours of the image and then fill that image with particles and then had those particles be the colors of the image? Could you paint a picture that way? Could you make an installation where the attraction particles are where the user's hand is? There's so many possibilities here. So I hope you make something with this and discover something interesting and make it and share it with me in the comments or on Twitter at Schiffman. If you have any complaints, please send them. I don't know where you should send them. Send them to me, I suppose. I can understand you having a lot of complaints after watching this particular video, but I'll see you in another episode of The Coding Train.